Right, hello, and I hope you're well. So I'm John, I run A-levelmathsrevision.com. So just going to go through today, just to keep you going while lockdown's happening, going to go through trig identities today. And we're going to go through it from the perspective of trying to master it. So trying to actually, we'll start off from basics, but we'll quickly get more difficult and go for the real top-end questions. So first of all, just type something in the chat if you can hear me. So hamster, hi. Yeah, brilliant. That'll do me. So, we'll get started then. Hi Emily, hi Heather. Right, so, first of all, let's define the trig identities that we need to know for Year 1 A-Level Maths. So the first one, and it's tan theta, and we've just got to learn these. Tan theta is identical to sine theta over cos theta. And the second one is sine theta squared plus cos theta squared is identical to 1. And this triple equal sign is a lot more, it's a lot stronger a statement than an ordinary equal sign, because this is saying this occurs for any value of theta. So no matter what value of theta we choose, this statement's true. Likewise here. But this statement here isn't quite how it's written. The more conventional way of writing this, sine squared theta plus cos squared theta is identical to 1. But I wrote this one first because that's just what it means. So that means sine theta times sine theta. That means cos theta times cos theta. So sine of theta all squared plus cos of theta all squared identical to 1. Let's just show that in action. So sine of, and let's pick daft number 25.6 squared plus cos of 25.6 squared, press equals and we get 1. So that's that in action. So let's show how these can be useful in solving equations. So let's take, for example, e.g. solve for 0 less than or equal to theta less than or equal to 360. And let's say we're solving 2 sine x minus cos x is equal to 0. So there's two possible identities we could use here. There's this one or this one. Which one do you think? First or second? Which one's most applicable? First one or second one, and why? Type in the chat, first or second. First or second. So a bit of mixed opinion there. Some of you saying first, some of you saying second. So basically, what the way I decide how to choose either the first or the second is, first of all, look at this. Are there any squared terms in there? Does it at any point say sine squared x or cos squared x? And in this case, it doesn't say sine squared x or cos squared x, so we wouldn't use the identity with the sine squared or cos squared in. And what I'm just going to do here is modify the question slightly, because that there should have been an x rather than a theta. There we go. So if there's no sine squared term in or cos squared term, then we probably don't want to use that identity. So we're going to use this one here. So I've had a few good suggestions in there. So my first thought here, I can turn this into a tan x by dividing everything by cos x. So if I decide to divide both sides, all terms, by cos x, like this, like that, and 0 over cos x, all the terms on both sides, then that means that using this identity here now, sin x over cos x is tan x. That becomes 2 tan x minus 1 equals, and 0 divided by anything is 0. So 2 tan x equals 1, which means that tan x equals 1/2, like that. Correct, tan x equals 1/2. So getting a lot of right answers in the chat there. Right, so now what we're going to do is we're going to inverse tan, we're going to arctan both sides. So arctan is another word for tan minus 1 or inverse tan. So our inverse tan of our arctan both sides, x equals arctan of 1/2, which is equal to, yeah, let's see. So arctan of 1/2 So what I've done there, my calculator is actually in the wrong mode. My calculator is actually in radians. I'm going to change that back into degrees there. So angle unit, degrees, and try again. There we go, 26.565. And a tip to gain as many marks as you can in an exam, don't over-round too soon. So try and keep it with as much precision and accuracy as you possibly can. So I've done 5 significant figures there, knowing that the exam boards probably want 3. So again, in the chat, I'm seeing a lot of right answers, and this is the process that we should go through. So all the answers were 0 and 360. So let's draw the tan graph. Like that there. Then there's another asymptote there. Like that. And we've got one there. So it was arctan of 1/2. So let's say 1/2 is roughly there. So we've got our first solution there and our second solution there. So as I said last week, imagine somebody standing at the beginning of the graph and they have to walk a distance of 26.565 to get the first solution. So to get the second solution, the person standing at the corresponding part of the graph there has to walk the same distance. So it becomes 180 plus 26.565. Equals. So now let's give the answers to 4 significant figures, say. It's not specified, so 26.57. And add 180. 4 significant figures, 206.6. And there's our 2 answers. And any good answer will have the answers grouped together in a box at the end, just to screen out to the examiner that you want them to mark that. So let's do another example. So we're starting off, as I say, a bit basic, but we'll quickly ramp up the difficulty level. E.g., solve for 0 less than or equal to x less than or equal to 360. Let's solve 2 sine squared x plus 3 cos x equals 3. And remember, we've got our 2 trig identities here. Let's bring them down. So I'll copy those and try and put them next to every question. And this is a good way of learning them, to practice just writing them next to every question. So this time, as I said before, we're looking for which of these identities to use. If you see a sine squared or a cos squared, chances are it's the one involving sine squareds and cos squareds like that. If you don't, chances are it's that one there. So this sort of looks a little bit like a quadratic, but not quite, because the terms are different. We've got sine squared x there and cos x there. We can change this sine squared x into a cos squared x using this identity here, using a rearrangement of it. So this identity here implies that sine squared x is identical to 1 minus cos squared x. So actually we can use that identity there and replace that sine squared x with 1 minus cos squared x to turn it into a quadratic where everything's in the same term. So 2 lots of 1 minus cos squared x plus 3 cos x equals 3, which implies that 2 minus 2 cos squared x plus 3 cos x equals 3. And let's make this look more like a quadratic. So we'll have the squared term at the start, minus 2 cos squared x, the cos x term in the middle, and let's take 3 from that side, which means take 1 there, equals 0. So you can factorise if you want, in which case I'd advise timesing both sides by -1. However, I wouldn't advise doing that because it doesn't say show full working in the question. Therefore, it's fair game to use our calculator to solve that quadratic. So we're finding solutions in cos x. So it's a polynomial, degree 2, minus 2 cos x plus cos squared x plus 3 cos x minus 1 equals. So here I see that cos x equals 1, or cos x equals, and let's see what the other solution is, 1/2. So now we've got two equations, two separate equations to solve. So x equals arc cos of 1 and we should know these. However, take no chances in an exam. Arc cos of 1, which is 0. Don't risk misremembering stuff. And x equals arc cos of 1/2 which is equal to 60. So we've got all those solutions to find now, all between 0 and 360. So rough sketch of the graph. Arc Oscar means inverse, so that means exactly the same thing as that there. However, it is terminology that you need to know. So you do need to know that, but it just means inverse. The reason that I prefer using the terminology arc cos instead of cos -1 is because sometimes in some uses of that power -1, it can mean inverse or it can mean reciprocal. So I try and avoid all the confusion just by calling it arc cos so people know what I'm on about. So cos graph like that. So arc cos of 1 is 0. So there's our first point there, right at the beginning. So there's an answer at 360 as well, the corresponding side of the hill. Then, let's look at a half. So the first one is 60 degrees. So someone standing at the beginning of the hill has to walk 60 degrees. So likewise, the friend has to as well. So we've got x equals the solutions that pair with this one, 0 and 360. And then we've got for the other one, 60 and 360. Take 60. As we can see, he has to walk 60 degrees in that direction. which is 300. Now, I often get asked, should you write the answers in order? And I actually think not. And the reason I think not is because the mark schemes typically cluster the solutions depending on which equation they came from. So you're making the life of the examiner easier by grouping them in terms of the equation you found them in. So here's one now to try and catch you out. So let's do 3 sine x. So starting to get more difficult now. 3 sine x minus 2 tan x equal to 0. And there's the possible equations that we can use. And we want all the solutions between 0 and 360. So judging by the rules and using the rules I just told you about which one to use, which one do we think is more appropriate? The first or the second? Type it in the chat, what do you think? Tiny bit of a delay, so it'll be about 10-15 seconds before I start seeing them. So I'm seeing a lot of people typing first, and yes, I quite agree. Yes. So we're all there. We're all there. We're all seeing that's the first one. That's progress, is that? I like that. So let's use it. Let's take tan x and turn it into sine x over cos x. So that means that 3 sine x minus 2 sine x over cos x equals 0. What next? Any ideas? Yeah, times... So I feel a bit daft saying a name, planted shrimp, but I'll go for it anyway. So planted shrimp says times 3 sine x by cos x. So I'm going to elaborate on that. That's a good idea. But I'm going to say times everything by cos x times all terms by cos x. So that gives us 3 sine x cos x minus, and times in this by cos x undoes the divide by cos x, minus 2 sine x equals 0 times cos x, which is just 0. And this is the part where I'm actually going to do something wrong here. I'm going to show you the wrong way to do this and explain why it's wrong. So notice that both terms have a sine x in common. Again, what I'm about to do is wrong. So I'll do the wrong bit down here. Divide both sides by sine x, which gives us 3 cos x minus 2 equals 0, which means that 3 cos x equals 2, which means that cos x equals 2/3. And that's wrong, because when you divide by something, like I divide by sine x just there, you're making a very bold statement. You're shouting from the rooftops that you're sure that sine x equals 0 isn't a solution, because you can't divide by 0. So you're saying, I'm 100% sure sine x in this equation cannot equal 0, so I'm going to divide by it. Well, in this case, that was a false assumption, because actually sine x equals 0 can be a solution. Exactly. So factorising it. So yeah, well done. Factorising it is the best idea. Never divide by a variable if you're unsure about whether it can equal 0 or not. So in this case, taking out sine x as a factor, we get 3 cos x minus 2 equals 0. And that leads to this solution here, cos x equals 2/3. which we want. But had we have just divided by sine x, we'd have lost this solution here, the sine x equals 0. You divided by sine x, being sure that it couldn't equal 0, but actually it could, so that messed that up for us. So when you get something like this, always factorise. Right, so now we've got x equals arc sine of 0, which is 0. So we can see that, drawing the graph, 0, 180, 360 are 3 solutions. And we've got, from this one, x equals arc cos of 2/3. So these are, again, what I'm going to do here is try and go through all the things that I could throw at you in an exam to try and catch you out. Arc cos of 2/3, which is 48.190. And draw the cos graph. So, like I said before, always start at the beginning of the graph. Has to walk 48.190 to get to that solution. So the friend on the other side of the graph has to do exactly the same. Walk 48.190 at the other end of the graph. So 360 minus 48.190. So our solutions are x equals 0, 180, 360, 48.19 to 4 significant figures, and 360 minus that, 311.8 to 4 significant figures. So there they are there. So that's basically a few things that they can throw at you. So what I'd like to do now is do a couple of proofs. So proofs are quite a difficult concept at AS because it's not really like much you've done before, these styles of proofs. So I'm going to throw this here. So it says prove that that's the case. And remember, the identities that we can use are tan theta is identical to sine theta over cos theta, and sine squared theta plus cos squared theta is identical to 1. So the wrong way to do this would be to write out both sides. This is almost like a joke you're telling, and this is the punchline, and your account of how you get the punchline goes here. But when you're telling a joke, you don't give away the punchline right at the start. You wait until the very end. So your very last thing to write should be that. So we can't times both sides by something because we're only considering one side. So I like to start my proofs by writing LHS, left-hand side, equals. And what I want to do now is multiply those brackets out. It's the only thing I can do. Sin x plus cos x, sin x plus cos x. But never refer to the right-hand side until the very end in a proof. Equals. Okay, so we've got sin squared x there. Got sin x cos x there. We've got another sin x cos x there. And we've got a plus cos squared x there. So sin squared x plus 2 sin x cos x's plus cos squared x. And every statement I write here is going to be equal to the previous line. This is all I've got to work with. I can't do things to both sides. I can't times both sides by whatever. I'm stuck with just trying to manipulate what I've got. So at this point, any ideas? We're almost there, but what do I need to recognise about this? what appears in this line of working here that will allow me to simplify it. Yes, correct. Sine squared x plus cos squared x is equal to 1. But what we need to do, often to get the marks, depends on your exam board, but yeah, depends on your exam board. We've got to jump through hoops. So actually, I'm going to write an extra line that you wouldn't have thought I would have had to have written. But quite often, they want you to explicitly, on mark schemes, show which identity to use. So, gathering those up, like that. And just underneath it, putting some braces, saying equals 1, that guarantees that you get the marks set by the exam board. So equals 1 plus 2 sin x cos x equals right hand side, and there's our punchline. It's equal to the right hand side as required. And that's how I think the best way of doing it. I think that's the best way of presenting a proof. So let's do another. And every time you do one of these, write out the identities so that you end up remembering them. Remember, be completely clear in which identity you use. So we've got two identities, remember. So a good way to remember them is just write them down. So tan theta equals sine theta over cos theta is identical to, in fact, and sine squared theta plus cos squared theta is identical to 1. They're the trig identities at our disposal. So any ideas on this one at all? Looks a bit more difficult. I can't see any obvious trig identities to use currently. Nothing jumps out the page at me. So roughly, I think a question like this would be worth 3, possibly 4 marks. More likely 3. And it would usually be the start of a question on solving an equation. So part 1 would say prove that this equals this. Then the next part would say use this to solve. So it will be part of a bigger, probably 6 or 7 mark question. But again, that's opinion. We'll have a look at some actual exam questions in a short while, so you can see for yourself how they're usually structured. So with this one, I'll give you a clue. Add these as fractions, or subtract as the case may be here. Try and combine these over a single denominator. So that's the case. 1 over cos x minus cos x over 1. So we've got 1 over cos x. And to give this a denominator of cos x, we're going to times both top and bottom by cos x. Both top and bottom by cos x to get cos squared x over cos x. So the left hand side equals that. Which is then equal to 1 minus cos squared x over cos x. Recognise anything now? Any ideas? Give 10 more seconds to answer. Yes, Emily, well done. The top of the fraction is the same as sine squared of x. Correct. So, I would just annotate that answer. Equals sine squared of x. So equals sine squared of x over cos x. Yeah, Heather, you got there as well? Okay. So now we want it equal to sine x tan x. So that's the same. If we split up the sine x on the top to say sine x times sine x and put the cos x there, then we've got it. We've got sine x tan x equals sine x tan x equals the punchline, right hand side. Let's do another. So as I say, these are pretty top end questions, so adding the techniques here to your repertoire can only be a good thing. So we've got the two trig identities I've just highlighted here. They're the ones at your disposal. Any ideas on that one? And with these proof questions, we'll just say left hand side equals. With these proof questions, sometimes it's just doing something in vain hope that it's going to make it look a bit easier. You won't always get it right, in which case you go back and do something else. There's not really a way of knowing 100% that what you're doing is right. You've just got to experiment. So is there anything at all with this one we can do? Right, so multiply 1 minus sin x by the left-hand side. Unfortunately, there's only one side to this, so we can't do any multiplying of anything at all. We're stuck with what we've got. We can't say do this to both sides, or we can't say do that to both sides. Unfortunately, we can only change that what we've got there, represent any of the terms. So with this one, again, the right-hand side's the punchline. So we can't refer to the right-hand side until the very end. So this here, and this is why I'm doing this. These are loads of misconceptions that people have with proofs. So we're just trying to plug that gap now. So cos squared x is 1 minus sine squared x. That's the only thing that I possibly can do, and I'm just doing that in hope. Yeah, Emily, you got there just as I was saying it. Good. Like that. So we can only work with the identities we've got. As I say, we can't do something to both sides because it's asking us to work from the left to the right. And this is with this question, what I'm going to call the clever part. Notice that this is the difference of two squares. So, if I factorise it as 1 minus sine x, 1 plus sine x, over 1 minus sine x. I can see that I get a 1 minus sine x over 1 minus sine x. So if I just move that to illustrate that, if I put that there, I can see that 1 minus sine x over 1 minus sine x is 1, leaving me with 1 plus sine x. So that's a little bit on proofs. So let's put that into practice now. Let's do a couple more proof questions. So let's take an exam question. This one was from 2010, actually. I do like the old spec exam questions. As you know, as you've probably seen, I've put them and categorised them on my website in line with the new spec, because I just think they're a good way of practising questions by topic without wasting papers. I think there aren't that many exam papers so far out there, so I think to tackle them in full nearer the exam is a good thing, rather than picking out questions. So I've turned all the old spec papers on my website into questions by category. So this is the question that I would like to look at now. So it's asking us to show that sine squared x minus cos squared x over 1 minus sine squared x is identical to tan squared x minus 1. And remember that the trig identities that we can use, tan x equals sine x over cos x, and sine squared x plus cos squared x equals 1, and I'll make those identity signs as well. So have a think about how you do that one. Maybe have a go at it. There's going to be a little bit of experimentation involved. Just do something, hope it's right. If it makes it more complicated, chances are it was the wrong thing. Just go back and try again. Give you a couple of minutes on that before I have a go. Feel free to type any of your ideas into the chat. You're on fire here, Emily. I think I agree that 1 minus sine squared x on the bottom is screaming out to me as being wanting to be changed into cos squared x. So, left hand side, and that's all we've got to work with, don't refer to the right hand side, equals sine squared x minus cos squared x over 1 minus sine squared x. And that there's cos squared x equals sine squared x minus cos squared x over cos squared x. Looks like we made a bit of progress there. Any ideas from that point? Any ideas? Okay, I'll give you a clue. Again, it might be the chat delay. You might have typed something. It might take a little while to get to me, but I'll give you a clue. This means divide each of the terms on the top by that. So it's asking us to divide both of them. So if I split up the fraction into two separate parts, I get sine squared x over cos squared x minus cos squared x. Yeah, Emily, you probably typed that before I started saying it. It's probably the chat delay that's done it. So well done. Like that. So that's sine squared x over cos squared x. Well, it's the same as saying sine x over cos x squared. So that's tan squared x. And again, I'm probably going a bit overboard annotating my answers, but just like to be safe, tan squared x minus 1 equals the right hand side. Right, so hence solve that equation. We've proved it. Let's go on to solve that equation. So notice that what that is there is what we just proved to be equal to this in the first part. So we can replace this with the first part. So we've got tan squared x minus 1 equals 5 minus tan x. That's a quadratic in tan x waiting to be solved. So I'll give you 30 seconds, a minute to get on with that, then I'll have a go. Right, so I'm just going to quietly get on with this. No pressure to solve it by factorisation. It doesn't say show detailed reason or show full working. So you can factorise if you want, or you can use your calculator just to solve it. For a bit of a change, I'm going to factorise it now. So this first solution here, there's an issue because that doesn't fit on our graph. Our graph only goes from 0 to 360, but we don't discard that because whilst that doesn't, whilst it itself isn't a valid solution, if we put it on our graph, if we extend our graph a little bit, we can see that it leads to some other solutions. So -3 roughly there. So we've got that one, which we're going to discard, but it leads to these as well. Yes, a hamster, good. It's minus, so we'll extend the graph. So you remember that from last week, good man. So it's 71.565 to the left. Likewise for these ones here. So 180 minus 71.565 is 108.435. And 360 minus that gives us 288.435. We'll discard that one. And 63.435, well, arctan of 2, so 2 is roughly there. So this person here has to travel 63.435 from where he stands, so this one the same amount, so 180 plus 63.435. Which is 243.435. Therefore, concluding, and remember, cluster our answers up, an examiner's looking for you to conclude. So we've got 108.4, 4 significant figures, give them a bit more than 1 unless they specifically ask for it. 288.4, 63.44, and 243.4, and there it is there. Let's have a look at another one. So this one, sort of, it's very subtly different to the type of proof that we've just been doing, because it says show that the equation here can be expressed in that form. So it's not an identity anymore. We're not proving that things are identical. This is an equation, keyword equation, with 2 sides. So at this point we are well within our rights to start moving things from one side to another by timesing or dividing. It's an equation, not an identity. And I just want to go back and show you the distinction. So this one is saying show that this is identical to that. So we start with the left hand side and work to the right. Identical, 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 there. This one isn't, says it's an equation, not an identity. So moving things from one side to another, it's fair game in this one. So take a few minutes on that one. See if by moving things around, and hopefully by this point you remember your trig identities. Those 2 identities, hopefully you remember them. Start moving stuff around and see if you can get from here to here. No problem at all. Glad you liked it. Hopefully see you again next week. And if you want to see the rest of it, it's going to be recorded and left on YouTube. So, sorry you've got to go, but enjoy whatever you're doing. So the rest of you will continue. So this first one, not sure how you've done it, but what I notice here, my train of thought, is that there's only tan squared x's and tan x's here. So I've got to do everything I can to get rid of the sin x's and the cos x's. I know I can turn this, get a step closer to it, I can turn this into a tan x by dividing by cos x. So in fact, if I divide all terms by cos x, so sin x minus cos x, just copying the question out, equals 6 cos x over tan x. If I divide everything by cos x, I end up with sin x over cos x minus cos x over cos x equals 6 cos x over tan x, and as a cos x goes on the bottom because I've divided by cos x. So basically I've multiplied the denominator of every term by cos x. That's the same as dividing by cos x. And hopefully this has made it obvious, because sin x over cos x, if I write it underneath like that, tan x, it's obvious which trig identity I've used. Minus 1, and cos x divided by cos x is 1, we might as well not write that, equals 6 over tan x. So there's so many different acceptable ways of doing this, but that's my preferred way, to identify first of all which terms I need and use that to get rid of ones I don't want. So now multiplying by tan x, I get tan squared x minus tan x equals 6, which means that tan squared x minus tan x minus 6 equals 0 as required. So we've done part 1. But even if you couldn't do part 1, which for 2 marks is a bit stingy to be honest, but even if you couldn't do part 1, part 2 is now doable, because it's given you the identity can be it's given you the equation here can be expressed in this form, so you can just use part 1 even if you didn't manage to prove it. Just use part 1 and solve that to get 4 marks. That can't be bad. So instead of writing this monstrosity here, tan squared x minus tan x minus 6 equals 0, and try and solve that. And we've solved one very similar to that. It might actually have been that exact equation was solved earlier. No, I think that one had a plus in the middle, actually, the one we solved earlier. So have a go at that. I'll give you 30 seconds. Okay. So tan x minus 3, tan x plus 2 equals 0, which means that tan x equals 3 or tan x equals minus 2. And hopefully by this point you're starting to see that these questions are getting a little bit repetitive. You start getting a bit bored of doing them because they're all the same, and that's a brilliant place to be. When you do questions, when you do the same type of question over and over again, you start to see that year on year there's not that much different that they can ask you. So getting bored of getting them right, I think that's a brilliant place to be. X equals arctan of 3 equals, and x equals arctan of minus 2 equals. So arctan of 3 equals 71.565. And probably to save time, I should stick with this one rather than do the other one. Like that. So arctan of 3, let's say that's roughly 3, so I can see there's 2 solutions there. So always start at the beginning of the graph. He has to walk 71.565 to get to that. So starting at the corresponding place does exactly the same. So 180 plus that. Thank you, Zane. I'm sure you're right. Let's see if I can get there. You beat me to it. $251.565. Did it ask for any number of decimal places as well? It didn't, so yeah, your answer's absolutely brilliant, it looks like. And arctan of minus 2 is minus 63.435. And we're going to have to extend the graph here. We can see that that one is 63.435 to the left, so it's to the left of that, and also to the left of that. So 180 minus 63.435 equals 116.565. And 360 minus that equals 296.565. And then finally, summarise your solutions. So 71.57, 251.6, 116, we'll cross that one out, 0.57, and 296.6. Box around them. So just in the chat here, what I'm doing, I'm going to type the link to where I've put all my categorised exam questions, because I think this is really, when you're revising, the technique you should use. So I think you should be doing questions by category before you attempt exam papers. Make sure you're mastering all the individual topics. Then when you get to doing the exam papers, I think when you hit a question you can't do, you should then stop and go back to the questions by category. So that's where we'll leave it for today. I hope you found that useful. And I'll be doing the same thing again next week. And as this will be happening every Tuesday until the schools are back open again. So I'm going to put a poll on Twitter. And the Twitter handle is, I'll type it now. That there. And I'll put that in at some point, hopefully this evening, and you can vote on what the next topic's going to be. I know we've had a few suggestions about practical differentiation. We've had logarithms, so I'll put another poll on there and you can decide. So take care, have a good week. See you next week.